Hi, and welcome back. Let's take a look at more Earth-Sun relationships this week, cluing in on the solar angle. So in the previous lab, we used the analemma to determine the sun's declination, or the zenith, or the latitude of the subsolar point. All those are the same, for various locations and dates. Here's our analemma again, and you already have downloaded, or you can find it in the course files. And one particular aspect, no pun intended, of today's lab relates to the tangent rays, so the solar beam that is parallel to the Earth's surface. This is measured at local noon and situated at 90 degrees latitude north and south of the subsolar point. It identifies areas that receive 24 hours of daylight and 24 hours of nighttime. It's always situated poleward of the Arctic and Antarctic circles. So to visualize that a little bit more here, we have tangent rays poleward of the North and South Pole. And sometimes it can be a bit different to view the Earth on this orientation, with the tilt of the axis being shown. So the might be drawn at first to visualize the equator as, straight left and right here, but actually this line is the equator because of the angle of the axis off the plumb line at 23.5 degrees. So in this case, right here would be your subsolar point, and these are the tangent rays. But in this lab, we're going to use the analemma to identify the sun's declination or the latitude of the subsolar point, as well as calculate the altitude of the noon sun for a given latitude and date. Okay, it's very similar to what our objectives were there. So this solar angle, or the altitude of the noon sun, can be determined using the following formula. Solar angles equals 90 degrees minus the arc distance. And the arc distance is found by taking the LP, or the latitude of the place, in consideration of, sometimes that's going to be addition, sometimes subtraction, of the subsolar point. So it's a little bit different just to have a bidirectional arrow there, but we'll see why that is more in a little bit here. In total then, in a little bit of Spanish coming out there for you, right? In combination, or therefore, we could say that solar angle is equal to 90 degrees minus latitude of place in consideration of, or minus / plus the subsolar point. It'll become a little bit more clear when we work it out here. Here's just written out what I just said. The solar angle in arc degrees above the horizon at noon is your solar angle. That's equal to 90 degrees minus the arc distance between your latitude, quote unquote, the latitude of place, or the LP, and the latitude of the subsolar point. So here we just have it written out again. And I find these things are a lot easier when we visualize them and with a graphical representation, and I think it helps to contextualize it a little bit more in terms of why this is valuable. In particular, why it sets the foundation for many other, why it's valuable in terms of how it sets the foundation for many other technologies that utilize these calculations. Originally, or going back some years, these all would have been calculated by hand first in consideration of of any number of cartographic or mapping, besides just mapping, directional navigational tools. These days, many sorts of computer technologies, digital technologies will calculate them, but it's a lot more useful to be able to use these types of GIS technologies if we understand at a very foundational level the formulas and the logics that go into creating them. So that's my attempt at describing, what the purpose of this is. Why spend, a lab figuring out solar angle? If anything, if that still doesn't do it for you, if anything, we can think about how cool it is to figure out different angles and positions at different times of year, particularly in different hemispheres. It's pretty fascinating to think about the relationship between our sun and Earth in terms of the massive amount of effects that it has on our weather, on our seasons, therefore on our climatology, therefore on humanity and our ecosystems. So maybe that's spanning out even further, but to bring it back to the image that we have in front of us here, and where my little tangent ray started from, is taking a look at solar angle, in this case based on 40 degrees north. So about 40 degrees north in California would be right about at Eureka, Arcata, up in Humboldt County, and numerous other cities and towns as we work east or west from there around the world. In terms of coastal California, that's where we could visualize ourselves being on December 22nd. And the location of 90 degrees solar angle, 90 degrees sun, is 23.5 degrees south on that day, right? Which makes a lot of sense because that's the winter solstice. And we know that on the winter solstice, the sun is in direct alignment with the Tropic of Capricorn. 23.5 degrees south. That's a little typo on the image there. So, calculation step 1, the distance in degrees between 23.5 degrees south and 40 degrees north. We add those, since they're two different hemispheres, equals 63.5 degrees. So we can imagine that across the Earth there, across the curvature. Step 2, 90 degrees, take away the 23.5, gives us 26.5 degrees. So that's the noon sun angle, the solar angle at 40 degrees north, or latitude of place, right, or LP, on December 22nd. And what's really neat here is to look at our sun's rays here mapped out or graphed out in yellow, and you can almost visualize, not that we would know just without the numbers there, that would be 26.5 degrees, but it's neat how the image helps us to corroborate or to visualize that. We can see how that makes sense, 26.5 degrees there. Versus, if we were to see this type of angle, obviously that's pretty familiar to us, being a 90-degree angle, but let's see let's imagine if something was telling us that the opposite side of the angle here, this little arc, was 26.5. We'd be like, no, that doesn't make sense. So one of the values of an image here, of a figure. So that's how we calculated our solar angle for December 22nd at 40 degrees north latitude. Arc distances, determining the arc distance between the latitude of place and the subsolar point. So in this case, that's referring to the between, I bounce back here for you, but between the latitude of place and the subsolar point. So in our previous slide, that would have been between Arcata, or Eureka for that matter, 1 degree of latitude covers a fairly large distance on Earth, right? So like various different cities, but latitude of place 40 degrees north, and the subsolar point, which was the Tropic of Capricorn, 23.5 degrees south. So the key thing to remember here is that it's hemisphere specific. What I mean by that is we subtract the smaller from the larger of the two latitude values when they are in the same hemisphere. This would not be the case in our previous slide there. That's coming up in the next one. And we add the two values together when the latitude of place and the subsolar point reside in the opposite, the north and south hemispheres. This is the case in our image from 2 slides back, right, where our subsolar point was in the southern hemisphere and our latitude of place was in the northern hemisphere. So we would need to add those two values to two latitudinal values to come up with the arc distance, because just by logically we can think of you're needing to cross the equator, versus if you're in the same hemisphere, then you're taking one away from each other, subtracting, because you're not crossing the equator. And we'll flesh this out together here as the slides go on. When calculating the solar altitude is equal to the solar angle above the horizon, north or south. And it's important to remember that the solar altitude is not a latitude. Okay? It should be expressed, and it should be not expressed as a latitude. So for example, solar altitude equals 12 degrees south. No, that's incorrect. The solar altitude is expressed in arc degrees above either northern or southern horizon. So for example, solar altitude equals 12 degrees above the southern horizon. It's because this is really an angle and not a latitude. It's a point in the sky, so to speak. It's not a latitude on the Earth. So, solar altitude. When subtracting the arc distance from 90 degrees, okay, if the arc distance is expressed as degrees and minutes, subtract from 89 degrees 60 minutes rather than 90 degrees 0 minutes. This reduces the common mistake of borrowing 10 arc minutes rather than 60 arc minutes from whole degrees, harkening back to a couple labs back there. Recall that there's 60 arc minutes per arc degree. So, similar to minutes in an hour, right? So how do you determine which horizon the solar altitude is above? Well, if the latitude of place is poleward of the Tropic of Cancer, solar angle must be above the southern horizon. Poleward meaning towards the North Pole in this case of the Tropic of Cancer, which is 23.5 degrees northern latitude. If the latitude of place is poleward of the Tropic of Capricorn, the solar angle, sometimes the slides are calling this solar angle, solar altitude, it's a pretty synonymous term, must be above the northern horizon. And we'll see this as we go on. But just to make a quick note on it, I guess you can, again, this is when it helps to visualize yourself being at a certain place on Earth, right? Putting yourself in a certain place, in a certain geographical, let's say a city for that matter, and visualizing where the sun would be. If you're So for instance, if your latitude of place is poleward of the Tropic of Cancer, to put ourselves back, well, even at DVC, right, north of the Tropic of Cancer, the solar angle must be above the southern horizon, right, because the sun doesn't arc that far ever in the sky that it could be north of that point, right? No matter any time of year, we're always looking south to see the sun there. If you encounter a problem while attempting to determine which horizon the angle of the sun is above, just draw a simple diagram. Okay, so here we are, we're south of the equator. Sun's hitting us there. And, sorry, we're not south of the equator, right? Going back to our 40 degrees north or even 37 degrees north at Diablo Valley College, there's our latitude of place, roughly. The difference between latitude of place and subsolar point is our arc distance there, right? This kind of helps us visualize why we would add those two latitudinal values. So you have the 37 degrees here, roughly, let's call it 23.5 degrees there, right? And getting back to our image, so we would add those two values. Versus if your subsolar point was north of the equator, it makes sense why we would subtract those two to come up with the arc distance. So, getting back to the drawing a simple diagram to figure out the solar altitude here, we have it drawn out now, and now we're switching our latitude of place to the southern horizon. Here we're both, again, hemisphere specific, so this is a case where we would subtract subsolar point from the latitude of place to figure out our arc distance. But what got us on this little image there is to figure out which horizon the angle of the sun is above. Okay, so if we're here, we can see why, and our subsolar point is down near the Tropic of Capricorn, and the subsolar point in the southern hemisphere. Our sunbeams are hitting there. We can clearly imagine, visualize that the sun is above the southern horizon. For our latitude of place, it's down in South America somewhere, southern South America. We can clearly visualize, imagine yourself standing right there, the sun's going to be above your northern horizon. That's a little tip for drawing out the simple diagram, as they call it. Okay, so let's write the formula and insert the variables that are given. We have solar angle equals 90 degrees minus the latitude of place, difference between the latitude of place and the subsolar point. So for example, if the latitude of place is 18 degrees north on February 9th, what is the solar angle? Okay, so solar angle equals 90 degrees minus 18 degrees north, the difference between 90 degrees north and the subsolar point. Subsolar point, going back to the analemma on February 9th, is 15 degrees south. At solar noon, that's where the subsolar point is. And these are different hemispheres, so you would add those, right? 18 degrees north is in the northern hemisphere, 15 degrees south is in the southern hemisphere. And again, we can kind of visualize that because we know in February, in the northern hemisphere, the sun's pretty far south, right? We're due to the tilt of the Earth, and where we are in the rotation, for that matter, of the Earth around of the orbit, the Earth around the sun. Anyway, for me, that helps think think these things through. Besides just making a mathematical formula of it, trying to position myself, oh, somewhere down in Mexico. I imagine maybe we're even south of Mexico. It's let's see, where's the 18 degrees? We'll call it 20 degrees north. This would be southern Mexico, or even further south. Let's say this doesn't have the exact 18 degrees line on it, but call it Guatemala for safety's sake. Not that, of course, those two countries touch, but it helps to map it out sometimes. Don't be afraid to take a break from these math questions and be like, yeah, where's someplace on the earth that I could visualize this from? So we'll keep going then. Right? 90 degrees, take away the 33. Right? Different hemispheres, so we add those. 18 plus 15 equals 33. 90 minus 33 is 57 degrees. Now we think through, right? So our solar angle, so the angle in the sky at noon of the sun. Right? We don't express this as a latitude. It's not 57 degrees north or south. It's just an angle in the sky. But we do think through, is it a solar angle above the north or the southern horizon? Okay, the solar angle must be over the southern horizon. So the correct answer is solar angle equal to 57 degrees above the southern horizon. Why must be above the southern horizon? Well, we're in the northern hemisphere. So, let that sink in a little bit there for you, and we'll go on to the next one. Next part of this. If the solar angle is 60 degrees solar altitude, in this case, in this case, we're going to solve for the subsolar point. It's like classic math problems. We figure out one part of it, then you move on to the next and figure out the next part of the equation. And this is we can think of this as quite valuable. Right? We wouldn't want to only figure out one aspect of the equation if we were sailing somewhere on a ship or navigating through the plains with only a sextant to study the stars with. Angle of the sun here. We go. Solar angle 60 degrees above the southern horizon, and the latitude of place, in this case, 15 degrees north again. We're going to solve for the subsolar point. So we have 60 degrees equals 90 degrees. Take away 15 degrees north, and the difference between that and the subsolar point. 90 degrees minus 60 degrees is 30. So to figure out what that 30, which 30, right? Because there's two possible ways of getting to 30. We could have 15 degrees north plus x or 15 degrees minus x. So we can therefore think through, to add up to 30, we would need to add a 15. That means, right, they would be in different hemispheres. We only add when they're in, the two locations are in different hemispheres, so that would be 15 degrees south. Or in this, we could also get to 30 by subtracting 15 from 45. In most cases we would see the 45 before the 15 there, but you see what we're getting at here. And because it's subtraction, be the same hemisphere. So north and north. But the subsolar point cannot be outside of 23 degrees, 23.5 degrees north or south. We know that, right? Winter equinox, well, let's just stick by dates. On December 22nd, farthest south the subsolar point hits is 23.5 degrees south, the Tropic of Capricorn. July 21st, on June 21st, 22nd, depending on the year, the farthest north the sun ever hits straight on Earth is on June 21st, and it's at the Tropic of Cancer, right? So that's why they're saying the subsolar point cannot be outside of this range. Therefore, we need to go with the 15 degrees south, because it couldn't be 45 degrees north. So it's that's how we get to the, I was about to say it's a bit of a brain twister there, but that's how we can eliminate one of the two possible answers. And here's another example. Okay, we're going to solve for the latitude of place, in this case, the third variable of the equation. If the solar angle is 42 degrees above the northern horizon, we're a little bit further north there, working up into southern Oregon in terms of coastal West Coast North America. Maybe right around the border there. Yeah, probably just north of just in southern Oregon. And the subsolar point is 12 degrees south. Let's see, where's 12 degrees south? We can vision that. Ecuador? Maybe into southern Peru, actually. Okay. To continue our coastal theme down the west coast, we have our 48 degrees. We have our 42 degrees equal to 90 degrees minus difference between our latitude of place and our subsolar point. So you have 90 degrees, take away 42, it's 48. And again, we have two ways of getting at the 48. We have x plus 12 degrees or x minus 12 degrees south. So LP is either 36 degrees north or 60 degrees south. Well, so I'm going to have to apologize there for solar angle. I made the classic mistake of associating 42 degrees with the latitude. Okay, I severely misspoke there. Solar angle, and it's a good example of how easy it is to associate degrees with a latitude. Solar angle is just the angle of the sun in the sky. It's not a latitude reading. I was wondering why we had another degrees here. And so, I apologize for that mistake. We're not in southern Oregon. We're either at 36 degrees north or 60 degrees south on Earth. Okay, either just south of DVC or down at 60 degrees south, pretty far down in the southern hemisphere. And it can't possibly be 36 degrees north. Okay, so the location of place is in fact down at we're in the water just north of Antarctica. This is the peninsula called the Antarctic Peninsula, and the southern. We might be on land actually in the southern Shetland Islands. And why can it possibly be 36 degrees north? Well, this is when we get to visualize where we are again, and we know that our solar angle is 42 degrees above the northern horizon. And if we were at Diablo Valley College, there's no way that the sun could be in the northern horizon. Okay, so that's why we've written here it can't possibly be 36 degrees north. So we've figured out all three of the equations, all three of the variables in the equation. Be sure to read the lab, complete the 20 questions, and let me know if you have any questions. Thanks a lot.